So in this example, we're going to look at finding some minimal sufficient statistics. So we'll begin by recalling how we find minimal sufficient statistics in general using Fisher's factorisation theorem. So basically, you want to get the ratio of the distribution in terms of x and y, and you look for when they are independent of whatever parameter you're interested in, if and only if the statistic in terms of x is equal to the statistic in terms of y. So this is a very simple way of finding minimal sufficient statistics. So we'll begin with our first example looking at the normal distribution. So in the normal distribution, if a single observation would have this distribution here. So if I was to do the ratio of a single observation of x to a single observation of y, we'd have f of x divided by f of y is equal to, well, this is to the power of minus a half here, so 2 pi sigma squared to the power of minus a half e to minus x, and then the x minus mu to be squared over 2 sigma squared, and the same but in terms of y at the denominator. Okay, basically you have something here that's the same above and below the line, so we can get rid of it and make it simpler. So we have the exponential, we'll write it like the exponential, and minus on the denominator becomes a plus on the numerator in terms of exponents. So we have y minus mu squared over 2 sigma squared minus x minus mu to be squared over 2 sigma squared. Now that's a single observation, but we're looking for something in terms of if we have more than one observation. So if we think in terms of a vector of observations instead, becomes the product of this I equals 1 to n of the exponential of what we've just have, yi minus mu to be squared 2 sigma squared is over, that's common, minus xi minus mu to be squared. And if we bring in this product, it becomes a sum. So we have the exponential of the sum of I equals 1 to n, and we squared these terms out. So yi squared minus 2 mu times the sum of yi plus n mu squared, and then we have minus the sum of xi to be squared because it's xi squared and then minus, so plus 2 mu the sum of xi I should say here, and minus n mu squared, and all of this is divided by 2 sigma squared. So we tidy this up a bit. So we have plus n mu squared minus n mu squared. So they will cancel each other out. So we simplify it. So we have and gather terms in so the sum from I equals 1 to n yi squared minus the sum from I equals 1 to n of xi squared, and then we have, let's say, plus 2 mu times the sum of xi from I equals 1 to n minus the sum of yi I equals 1 to n. And all of this is divided by 2 sigma squared. So this is constant with respect to mu if and only if the sum of xi is equal to the sum of yi. So the sum of xi is a minimal sufficient statistic for mu. And it's constant with respect to sigma squared if and only if, and you have two things here that have to happen. The sum of xi has to equal to the sum of yi, because this has to essentially disappear, and this has to disappear. And the sum of xi squared is equal to the sum of yi squared. So your minimal sufficient statistics for mu is the sum of xi, or any simple function of the sum of xi, for example, the mean, which is the sum of xi divided by your number of samples. And your minimal sufficient statistic for sigma squared is the sum of xi, I equals 1 to n, and the sum of xi to b squared. So that's how you calculate minimal sufficient statistics using the result of Fisher's factorization theorem.